Hey.
What is the shortcut to do the fractions on the TI-84?
Oh. Yeah, so if you want to do fractions, you're going to do second y, oops. Second y, and then you're going to see that n over d feature there. If it doesn't show up, then maybe, I don't know, your calculator may not have it. Let's see.
I found an interesting Oh, yeah.
All right, hello everyone. Today we're going to go over worksheet 2. We're probably just going to be able to have time to get through the first page, but I think that will be a good significant portion of what I wanted to do today. I'm calling this a non-calculator section. It doesn't mean that you can't use your calculator on the test. It just means that these are the types of problems that I'm looking for your steps to be spelled out. So I'm looking for you to show me your integral steps, your derivative steps, all that. The calculator portion, that just means that you can just make the calculator do the calculus for you, and that's all you need. So you don't have to show your work, because those are typically going to be more complex problems that we're going to just let the calculator do its work. But that is also a way to, that's more of that portion is like kind of yesterday, where I'm more concerned with, do you understand the concepts? Do you understand how to plug in the calculator? And do you know how to interpret the information that you gathered? Okay. Okay, so today, the problems, these are more kind of procedural, working through it by hand. But obviously, you can use your calculator to combine like terms, things like that. But just looking for steps here. So I'm going over worksheet 2, but I'm adjusting some of the problems here. So this is number 1. If you guys can adjust that problem here, this is a denominator. I'm making it 3 root x, and then the middle term, I'm making it square root of x to the 5th. Now, this was a problem that this similar problem showed up on your quiz, and there were enough common mistakes that I saw that I want to address it. Okay, so, but let's see. Let me see okay. But whenever we see integral problem, we always want to ask ourselves, is this something that we can do just by expanding? Now, this was on the previous quiz, so really this was the only option that we had. But really, it's also just a process that we want to go through, right? Treat every problem like as if this is option number 1. And we do see square roots. We know that radicals can be resolved. We know that the variable can be brought up to the top. But an expansion is doable because we don't have any ugly terms, any addition or subtraction of terms inside the square root. So this is not going to be an issue that we're going to have to require U substitution. So what I talked about before was that we need to move the square root of x up, but the 3 is going to stay put. It's going to stay in the denominator, so we're not going to move that 3 up. But this is the mistake that I saw with a lot of us, is when you guys brought your square root of x up, I think we forgot that there is this hidden parentheses that is still part of my numerator. And what I said was, when you bring that square root of x up, you're going to change that x to the -1/2, which many of you guys did. But I think many of us forgot to distribute through all these terms. And either I see students bring it up and made it just an addition problem after the 1, like 1 plus x to the negative 1/2, or I see students just multiplying with the 1 and not the other terms, but it needs to distribute to everything through. And I was thinking, well, a way to remedy that, since we're forgetting to distribute the square root through, what if we do it this way, so that we can remember that this 3 root x is really impacting every one of these terms. There's only one term in the denominator, so I can really just think of it as 3 separate fractions added together, right? It's like 3 separate fractions with a common denominator of 3 root x. So if I think of it that way, then we can write it out in a form that maybe is less conducive for these mistakes to happen. Now, if you were going through this method and distributing through, and you didn't have any issues there, then yeah, you can stick with that method. Okay, I just want to give an alternate method if we were having trouble working through this process that I shared earlier. So if we rewrite this as 3 separate fractions, these are the same things, right? It's like adding 3 fractions with a common denominator of 3 root x, right? I just add it, but I'm now splitting it up to make it suitable for power rule that I want to use. So I think this is helpful because now we can just think of it as, okay, if I just clean this up, if I clean this up, if I clean this up, then I should be able to just do power rule 3 times. Okay, so I'll convert all the radicals to be rational exponents. Now, here is the other mistake that I saw a lot, is many of us had trouble converting that radical to the appropriate rational exponent. You guys didn't have any trouble with square root of x. You guys all knew this was x to the 1/2, but this caused a lot of us issues. What is the rational form of square root of x to the 5th?
X to the 5/2.
X to the 5/2. Good. But this is what I saw. I saw a lot of this where many of you guys knew that there was a hidden number in this location. And so many of you guys were putting 1 here. And I think there's just a natural tendency to read from left to right. So you guys wrote 1/5 instead of 5/2. Okay. And the reason why it's 5/2, let's revisit what you do know. You knew that square root of x is x to the 1/2. The reason that's x to the 1/2 is because there's a hidden exponent to the right of 1, and then square root has a hidden radical of 2, or a hidden root of 2. The square root, right? We're splitting something in equal halves, and so the 1/2, we look at the number on the right before we look at the number to the left. So that's why it's x to the 1/2. So we can't all of a sudden change the rules and make it x to the 1/5. Okay, so this is a common mistake that I see here. Now, all right, let's go back to our problem here. We're going to try to get this all cleaned up, convert all the radicals to rational exponents. And now we still have to move all the variables up. So remember, when you move your x, the 3 is not going to go along with it. The 3 is already where it needs to be. We're just going to move the x up. So as you move the x, you're going to change the exponent, right? Make it a negative exponent. When you multiply your variables, you're going to be adding exponents. So 2 minus 1/2 is 3 halves. 5 halves minus 1/2 is 4 halves, which is 2. And negative 1/2 is going to stay. And I still see a denominator 3, which that's in the right place. But now I'm just going to push it out in front. Just make it a little cleaner for my power rule step. Okay, so this is where we need to be before we apply power rule. It needs to be cleaned up to this point with no radicals, with no variable in the denominator, with no parentheses. And now we can apply power rule. Now we can add 1 to the exponent, divide it by that new exponent, or that new exponent value. And as soon as you apply power rule, make sure that your integral and your dx notation drops out. Right? We've already applied our antiderivative. There's no need to indicate the notation of integral and du or dx, and then don't forget plus c at the end. Okay. And I also was cleaning up these complex fractions. So flipping the 5/2 as 2/5, flipping the 1/2 as 2/1. Okay, any questions with 1? Okay, give you guys another minute. All right, anybody still need to look at this? All right, number 2. Integral of 2x squared of 1 minus 3x squared. All right, first things first. Is this a problem that we can just rely on expansion power rule?
Oh, we might have to use substitution.
Okay, and why is power rule expansion not sufficient?
There's multiple terms.
Good. Right. Anytime I see 2 terms being added or subtracted into the square root, that's a red flag. That means it's stuck. It's stuck with this form. I can't combine these 2 terms together and resolve it and distribute the 2x through. Okay, so, but we always want to consider power rule expansion as first option. So that's why I keep doing this, because I don't want us to just assume that everything is going to be U substitution. And that's when we're going to run into issues. When it isn't a U substitution, you're going to go down the wrong path, and it's going to be hard to figure out that is not a U substitution problem. Good. So this is definitely U substitution. We explored our first option. It doesn't work. So if we want to do U substitution, we need a set of parentheses. Right? So how can we get a set of parentheses to show up?
Put the thing inside the root to the 1/2 instead.
To the 1/2. Yeah. Okay. Once you get a set of parentheses to show up, then you know exactly where to look for your U value. Okay. Sometimes there may be problems with multiple parentheses. If that's the case, then you may have to kind of do some trial and error to decide the appropriate U value. But in this case, for most problems, usually just one set of parentheses, and that's usually a good place for us to look for our U value. All right, so we see our U value be 1 minus 3x squared, and I like to underline the parts that I am focused on. Those are the parts that I'm looking to replace initially. Okay. There are other parts of the problem that may be issues, but we're going to let the dust settle before we consider what to do with the rest. So our focus is just making that U substitution and then finding a way to get that dx to be replaced. A piece at a time, we're just trying to get everything to be in terms of U and du. Okay, so we're trying to remove x's from our expression one at a time. Okay, so we let our U value be 1 minus 3x squared. We're going to find the derivative. We always do du over dx. 1 goes away to 0. Negative 3x squared becomes negative 6x. Cross multiply. Solve for dx. And now we have a clean substitution for our initial parts we want to replace. Okay, so as I make my substitutions, I'm going to carry down the parts that's not ready yet. So the 2x I'm going to bring down, the 1/2 I'll bring down. I'm just making my substitutions for those parts. Okay, so the 2x comes down, parentheses gets replaced with u, the 1/2 stays, dx gets replaced with du over negative 6x. Now, we look at what we have remaining, and we ask ourselves, can the x's go away on its own? Okay, and they do, right? Numerator, denominator matches nicely. So we're getting closer to our goal, but we have some coefficients that we want to kind of push out of the way. I mean, we got to keep track of it, but I like to push it out in front. I'll make this 2 over negative 6. I'll have it sit outside of my integral. And once you do that, you should be able to get a perfect match with this problem. Okay, we want this to be a perfect match. That way we know that we're ready for power rule. Negative 2 over 6 just reduces to be negative 1/3. And now power rule. Okay. Add 1 to the exponent, divided by the new exponent. Complex fraction, I can flip that to the top, make it 2/3. So I have my antiderivative. Do we stop there?
You have to put in, you have to replace u.
Yeah, so remember, your u is a temporary variable. It's going to help us through the process. It's going to help keep track of the coefficients. That's going to be part of our answer. But once we're done with what we need from our u variable, we're going to bring it back in terms of x. Okay, so u is just a temporary variable. Okay, any questions with 2? Okay, does anybody still need to look at 2? Okay, here's number 3. Five root x, parentheses, 4 minus 3x squared. All right, let's look at how this is set up here. Always consider option 1 first. Can we rely on those conditions to get it ready for power rule? What do you guys think? Actually, we can. Why is this able to resolve, but the previous ones were not?
Because in parentheses, it's not finished.
Right. The only exponent that is still suitable would be 2, right? We can FOIL it out, but if it's an exponent of 3 or higher, or if it's like 1/2 or 2/3, then we know we're stuck. But this is nice and clean, right? There's nothing that's preventing us from being able to distribute through. So just because you see parentheses doesn't mean that it's a u substitution problem. And second, just because you see square root doesn't mean it's a u substitution problem. This square root is okay because there's no additional terms that's added inside the square root, right? It's just square root of x. I can make that x to the 1/2. It's just a variable I can cleanly distribute through. So be careful, right? Look at your problem carefully, and don't let the parentheses allow you to make that assumption that it's just going to be a u substitution problem. Okay, if you go down the u substitution path, you're not going to be able to get. It's going to be messy. It's not going to be able to work its way the way you want to, and it's hard to revert back to thinking about power rule because we've already kind of gone past that step. So always consider option 1. Okay, so this we can just rely on just distributing, expanding, no need for u substitution. So I'm going to expand using power rule. Rewrite that square root of x, that's x to the 1/2. distribute through. Remember, when you multiply your x's, you're going to be adding exponents. So once I'm at this step, all my conditions are good to go. No radicals, no denominator variable, no more parentheses. We're ready to do power rule here. Okay, no need to revert back to my previous variable because I didn't do U substitution, so my answer is already in terms of x. So we can just leave it like that. Okay, remember that when you go through power rule, you may end up with some complex fractions below, so make sure you flip those up, resolve it with any existing coefficient, and then drop your integral and dx notation, and you'll have a plus c instead. Okay, any questions with 3? Okay, I'll give you guys a minute to copy down if you need to. Okay, here's number 4. Five x secant squared, 3x squared. All right, so one thing that stands out is we see some trig here. So we go to our trig rules and we ask ourselves, do any of these rules match? It's a little bit more complex than these rules, but maybe we see some foundational kind of outline that we can kind of work towards.
Secant squared u.
Yeah, looks like it could fit under that secant squared u umbrella, but obviously there's more things we got to keep track of. So, but I think, right, we have that outline there. We have that that basis there. So we're going to go through u substitution to get it to look like that rule. So what's our u value? Yeah, parentheses is already there for us, so naturally we're just going to go towards it. Now, can you see this working out nicely? What do you notice that's nice about this problem here?
The x value has an exponent that's 1 greater than the leading column.
Right, so that's a good sign, right? We know that this will work out cleanly. We're not going to have any issues where we have x's left over. So yeah, that's something that we can kind of predict. Okay, our u value, 3x squared. Go through our process here. And we are going to make our initial set of substitutions. (3x squared) gets replaced with u. Dx gets replaced with du over 6x. I'm going to bring the 5x down, right? I haven't dealt with that yet, but I've replaced my initial parts of the problem. Okay, we're getting closer, right? It looks a little closer than what we're after. What's next? Okay, cancel out the x's and good. Good. Coefficients can stay. That's not a deal breaker, but we do need to keep track of it. But once you push that 5/6 out, you should get a perfect match. And we are. We're going to get a perfect match once that 5/6 gets pushed out. And then once we get a perfect match, we know we have a rule that's completely available for us to use. And don't forget, u is only a temporary variable. So let's bring that u back in terms of x. Drop the integral and dx notation, or integral and du notation, and then don't forget about that plus c. All right, anybody still need to look at 4? All right, number 5. Integral of x squared, square root of 7 minus x. First things first. Can we rely on just power rule expansion? Okay, what's the issue? Yeah, multiple terms added, subtracted inside the square root. Okay, we can't do this. Okay, so option 1 is we explored it. It's not going to work. Second option is use substitution. So if we want to use substitution, we need to see a set of parentheses. So rewrite the square root as parentheses to the 1/2. And we know what to target. Our u value and eventually replacing that dx. All right, we're on the right track here, but what is not ideal about this problem? Yeah. I mean, this will be a lot easier if we can make this 7 minus x cubed, right? Then that'll be perfect. Then we know they'll cancel out, they'll be clean. So this just means that we got to do some additional things afterwards. We're not going to be able to quickly just get that x to go away. We're going to have to manipulate some things to continue to move forward towards getting that u to show up, or getting the x to be replaced in terms of u. So we just have to know that we're going to brace ourselves for some additional steps beyond an easier problem. Okay, so we let our u value be 7 minus x. We go through our steps there. We make our substitutions. So du dx, 7 goes away to 0. Negative x becomes negative 1. Cross multiply, move the negative over. All right, so this is where we are. X squared, unfortunately, does not cancel out because our u value does not have a degree that is high enough to handle that x squared. But we're making some progress. We've gotten some parts to be in terms of u, but this x is still unresolved. So what's available to us to help get that x to be replaced?
U equals 7 minus x.
Yeah, good. This is our key to getting that x to be replaced with something that is equivalent, but in terms of a variable that we want. So we'll rearrange this equation. We'll solve for x. I'll move this x to the left. I'll subtract the u to the right. X equals 7 minus u. I have a suitable replacement now. Replace the x with 7 minus u, but don't forget, it's still squared, so make sure you're doing 7 minus u quantity squared. The good news is we have everything in terms of u, but unfortunately, we're not ready for power rule just yet. We have to come back and we have to revisit, are these conditions resolved? Because if they're not, we still got to do them before we do power rule. So we still have parentheses in the way, we still have exponents in the way, so we have to algebraically clean this up. Now, my preference is I like to have my single terms in front and then my messier binomial afterwards, but that's just my preference. I'm going to just rewrite it this way. You don't have to. So I didn't want to lose track of my negative here, so I put the negative along with the u to the 1/2 in front and the 7 minus u squared. Okay, once I'm here, okay, careful with your order of operations. We can't distribute that u to the 1/2 through until you've taken care of that 7 minus u squared. So let's make sure that we FOIL this out. Now, after you FOIL this out, don't forget that you still want this to be in a set of parentheses to get it ready for that negative u to the 1/2 that still needs to distribute through. So yeah, quite a bit of algebraic cleanup that is still necessary even after you made your U substitution steps. So here's my expansion of my binomial. 49 minus 7u plus u squared. My combined like terms of 7u gives me 14u, but still leave it in a set of parentheses because we still have something outside of it that is still unresolved. Okay, we're almost there. Distribute the negative u to the 1/2 through. Make sure that when you're multiplying your variable u's, that you're adding your exponents. Okay. All this work, and now we're finally ready for power rule. Okay, add 1 to each of those exponents, bring down those complex fractions, bring them up, resolve it. And once you have everything resolved, don't forget your u variable is only temporary. You got to bring it back in terms of x. Okay, I'll stay on this page for a while so you guys can copy this down. Okay, any questions? Anybody still need this page? All right, let's look at number 6. All right, number 6. What about this problem is different than the previous ones? We have bounds. Okay, so can we just go ahead and put the bounds into the expression? Okay, that's something I want to make sure that we understand, right? The bounds, I know they're the first numbers that you see, but we don't want to plug in. If we plug in, we're just getting a bunch of ordered pairs on the function. That's not going to help us find the area or the antiderivative or the integral of this process. When we see bounds, you know that you're arriving at a number that is area-based, but to get to area-based value, we have to first have an area formula. So in order to have an area formula, we have to get it to the antiderivative first. So this is what I suggest. If you see an integral problem with bounds, rewrite it without bounds. You don't have to do it, but I just think that if you can look at the problem without the bounds, it kind of removes that distraction, right? You can focus on the task at hand. We're going to find that antiderivative first, and then when that is resolved, then you can look at the bounds and you can decide how the bounds is going to come into play. So I just find that this removes that distraction of the bounds, and you're not having to stare at those bounds and ask yourself, wait, did I miss something, right? Okay, so let's just solve this problem here. Okay, so treat it like a previous problem. We're going to revisit our conditions. Can we expand, FOIL, and just rely on those steps? Okay, why is that?
Because it's too good.
Yeah, it's a little high, right? I mean, it's doable, but you know, anytime we see higher than 2, we're just going to look at another option. Good. So we look for expansion. It's not suitable. It's not best case scenario. So option 2 is U substitution. So we already have a set of parentheses, so we'll just target our U value there. Is this going to work out nicely?
Yes.
Yeah, so this is nice, right? We see that exponent degree is 1 higher than x, so despite the fact that we're going to have to deal with the bounds, at least we're able to know that our U substitution process will go through pretty smoothly. All right, good. All right, we make our initial steps here, just like how we've done before. Let's not think about the bounds until we're ready for it. Derivative becomes negative 4x. Bring the dx up. Get the dx by itself. Okay. Transfer everything down. Just make these 2 simple substitutions, and then we can see where we are. So after we make our substitutions, we see piece by piece, we're converting our x's to be in terms of u. We still have x's left over, but just like what we expected, we're seeing that they will go away nicely. The degrees match, numerator, denominator. We do have to keep track with that negative 4, so I'm going to push that negative 4 out as negative 1/4. And now I have a nice clean power rule for me to apply. Okay, apply power rule. Clean up my coefficients. Now I have my antiderivative, and now I can consider bringing in the bounds into my problem, into my process. All right, so are we good up to this point? Any questions here? So we got to get to this point before we can consider anything with the bounds. All right, so we have an area formula, the antiderivative, which is now ready for the bounds. Now, there are 2 methods that you can apply from here forward. You can decide which one you want to use. On the test, you don't have to do both, right? You pick one, as long as you're picking one of the appropriate, as long as you're following through the correct path, either method is fine, okay? But I'm looking to see that you can apply these methods correctly. So I'll start with method 1. So method 1, I'm just going to get everything in terms of u. I'm going to leave this antiderivative in terms of u, and I'm going to adjust these bounds. Okay. Why can we not just use these bounds with the u to the 4th?
It's not in terms of x.
Not in terms of x. So that is one big mistake that I see. Students want to go ahead and put that 1 and 2 and half brackets and involve the u, but this is a mismatch, right? The 1 and 2 is in terms of x. This is in terms of u. Okay, we got to make them compatible. So first method is by converting the bounds. I'm going to leave this in terms of u. I'm going to convert my bounds in terms of u. So the key to help me get there is this assigned expression between u and x. Okay. So the way I'm going to convert the bounds, I'm going to take my original lower bound of 1, push it through this formula. So I get 1 minus 2 times 1 squared. That becomes 1 minus 2, which is negative 1. So my converted lower bound was 1, and now it's negative 1. My original upper bound was 2. I'm going to push it through this formula here, replace 2 in for x. I get 1 minus 2 times 2 squared. That's 1 minus 8, which is negative 7. So now my adapted upper bound is negative 7. Okay, any questions so far? Okay, I want to point something out here. so that you guys don't make a mistake if you go through this method. Some of you may be looking at this saying, well, my lower bound was smaller than my upper bound, but all of a sudden my lower bound is higher than my lower bound. So is that going to cause an issue? So what I want to say is, whatever your original lower bound position is, just put that number. Don't try to flip anything. Okay. So whatever starts as the lower bound, doesn't matter what it turns into, it's going to remain in that lower bound position. Whatever starts in the upper bound, you're going to put that in the upper bound position. Now, some of you guys may be looking at that and saying, wait, is that going to work out? Can I still plug in a lower value first? Things will work out. Okay, so the process will still work. If you get a negative value, then you get a negative value. That's the correct method. Okay, so I would say normally don't try to overthink it. Right, so whatever your value ends up being, just blindly place them where they initially were. So now that I have matching variables, my antiderivatives in terms of u, my bounds is in terms of u, I'm going to start my process, right? Start plugging in. Now I'm ready to plug in. So -7 goes in for u, minus, then we repeat the process for the lower bound, plug -1 in for u. Bring that up, you get -150. Now on the test and also on the AP exam, if you leave your answer in this form, that's perfectly fine. You will get full credit if you leave it unsimplified. But if you want to simplify it using calculator, you're free to do that as well. Okay, that's method 1. Any questions? The second method, I believe, is the method that a lot of students prefer. And that is where we get everything in terms of x. And I think the reason why students prefer this is because it's just a natural progression to bring everything back in terms of x, right? It keeps stressing that u is a temporary variable. So eventually you're going to bring that back in terms of x anyways. So you just go that one additional step, get that back in terms of x, make that substitution. And once you take that step, then you can just use the bounds in the original problem. There's no need to convert the bounds. And I can see why students prefer that method. And that's fine as well. Okay. You bring your antiderivative back in terms of x, and then you just use the original bounds because we already have a compatible value. But even though you may prefer this method, it's important that I teach you this first method because on the AP exam, multiple choice, there are problems where they are showing a problem worked out halfway through conversion of bounds, and if students don't understand conversion of bounds, they're not able to, because of the restrictions that they have in the problem that's presented to you, you have to know this method. So that's why I'm presenting this method to you. All right, any questions with number 6? Okay, we have time for one more. This is not on your worksheet, but I think this is a good one for us to see. It's a slightly different, so I think it's good to get exposure to this type of problem. So I'm going to call this number 7, but this number 7 is not the same as the one on your worksheet. Okay, so copy this down if you have to. This is integral of sine of x over cosine fifth of x. Okay, so the first thing I notice is, well, I got a bunch of trig functions here. So naturally, I'm just going to go to my trig rules, and I'm going to see if anything matches up. I do see a rule for sine. I do see a rule for cosine. But here's the issue. The issue is that we have to understand that these integral rules are extremely restrictive. So if I have anything attached through multiplication or division, we can't just pick and choose rules and plug in. These have to be standalone. The only thing that can happen is you can have addition and subtraction separating the terms, but if this is not a standalone term, we can't just apply the rule as we see it. So we have to recognize that this is too complex for any of these rules to handle. We know that we can't just jump into these rules, which means that we're going to have to rely on U substitution because this is too complex for any of these rules to manage. But if we want to explore U substitution, we would like to see a set of parentheses. So can we rewrite this problem with a set of parentheses?
Cosine x to the 5th.
Yep. This is a shorthand form of something that we did first semester, right? First semester I always said, hey, let's rewrite this so we can get it ready for chain rule. In this case, we're getting it ready for U substitution. Okay. We get a set of parentheses to show up, and once you see a set of parentheses, now you have a much easier time identifying your U value, right? Our U value is going to be cosine of x. We're going to be targeting that dx as well. Okay, so here we begin our first step. We let our U value be cosine of x. Now I need to find the derivative, so I need to go to my formula sheet, which also has the trig rules in terms of derivative. So du dx, if we look at our formula sheet here, cosine's derivative is negative sine. So we can begin our process there. Okay, u equals cosine x, du dx equals negative sine x. That's what our formula sheet tells us. Cross multiply, solve for dx, and we can begin to make our initial set of substitutions. All right, so this is what things look like after I make those substitutions. Sine x comes down, cosine x replaced by u to the 5th, dx becomes du over negative sine x. Thankfully, our trig functions matches and cancels out, right? So sine x goes away nicely. Keep track of that negative. So we're getting, at least we have everything in terms of u. That's a good sign, right? All the x's have been removed. So this is where I'm at right now. Okay, so I'm at this stage where I have my coefficient out in front. I have my variable in terms of u. Am I ready for power rule? Good, right. So we gotta be careful, right? We can't do power rule if u is out of place, right? So all these restrictive things that we have to be aware of, right? Just because that u is in the wrong place, we're not going to be able to get the correct answer if we do power rule. We got to move it up to the top, and the exponent that we need to be seeing is that -5. So yeah, just want to make sure we understand that, right? That it's tempting to just look at that going, well, it looks like I'm ready for power rule because my x's have been resolved, coefficients in front, I got my variable u, but we still got to do one more thing. That u is out of place. It's got to come up. Okay. Now, once it comes up, now we're ready. Okay, now we're ready. Okay. Add 1 to the exponent, divided by that new exponent. -5 becomes -4, divided by -4. The two negatives cancels out. I have my antiderivative. I'm going to resolve my negative exponent, so I have my answer. I'm just going to push that u back down to the denominator, and then I want to remember that my my variable u is a temporary variable, so bring everything back in terms of x. Okay, any questions? Okay, so Monday we will kind of put all this together. I will specify exactly what's going to be on the test. I'll put together a document that will spell out everything that we need to be aware of. On the test reviews, there are some problems that is not going to be on the test, so I will go over exactly what to expect, so you're not having to work on problems that is not going to show up on the test. And I'm also going to have help sessions Monday morning and afternoon, and Tuesday morning. They will all be recorded. Okay. All right. Have a great weekend. See you Monday.